Hi, I'm Yi Li, and today I'm going to present a topic on survey of 2D object detection. Well, here is the content. We'll cover the introduction, some related topics such as instance segmentation. There are several major tasks and challenges, and I will discuss 4 categories of approaches. Also, I will discuss future works, and finally the reference. First, object detection aims to locate objects and determine their category within an image or a video. The output of an object detection usually contains a series of bounding blocks and their corresponding category. On the left side, there is an example of a bounding block detected in the images. And on the right side, figure 2, here is the history of object detection. Before the introduction of the deep learning, the milestone of the AlexNet, most of the approaches are using traditional methods such as sliding windows and handcraft features. After the introduction of deep learning and deep convolutional neural networks, researchers are using image classification networks to extract features. One of the related topics is instance segmentation. The instance segmentation predicts bounding blocks, category, and pixel level mask at the same time. The instance segmentation models usually have an object detection head and a segmentation head. On the left side, we can see that there's 3 animals surrounded by the bounding box, and their color has been set to different category. On the right side, there is a fundamental pipeline of the mask RCN, which is introduced in 2017. Another topic is tracking. The object tracking aims to identify the location of objects and tracking their movement as they move across a sequence of frames. And the 2 classical object detection-based approaches are SORT, introduced in 2016, and Deep Sort in 2017. The second approach involves deep neural networks to train tracking networks. They both use the bounding blocks detected by the object detection networks to perform the tracking and re-identification. Now we will discuss the major tasks and challenges. I think the first task is the core task, the object detection, which we would like to discover the location of the objects and their categories. As for the traditional approaches, one of the challenge is the robustness of handcraft features, and another bottleneck is the accuracy of classifiers, for example FEM and AdaBoost. As for the recent deep learning-based approaches, the object occlusion and small objects are a new area. Also, the real-time inference is another task we want to achieve. For traditional approaches, the bottleneck usually in the sliding windows. And for deep learning-based approaches, the efficiency of feature extractor is very important. There are 2 images examples. For figure 6, it demonstrates the example of the object occlusion, and figure 7 is the small object detection, usually used in the remote sensing tasks. Now I will discuss 4 categories of approaches. For each category, I will discuss one method. For the traditional method, I will discuss the VG algorithm, which is the earliest object detection method. And second, I will discuss the faster RCN introduced in 2015. And after that, I will discuss the anchor-based one-stage method. A typical approach is YOLO series. And finally, the anchor-free method. As CenterNet is a classical approach. Now let's look at the first approach, which uses the integral image to speed up the detection process. And they will use learning classification functions such as AdaBoost. And they're also utilizing the cascade of classifier to improve the efficiency. Now let's look at the second deep learning based approach, FastRCN, which is a 2-stage method. For stage 1, they will do a region proposal, utilizing a selective search, and this also should be the performance bottleneck. And stage 2 is object detection stage. First, they will do the feature extraction, then mapping the proposed region to feature map, and finally, predict the bounding box and the class category. On the right side, there is a pipeline demonstration of this research. Let's look at the YOLO series, which is one of the most popular frameworks. For YOLO v1, the name of the paper is You Only Look Once, introduced in 2016. And afterwards, YOLO 9000 as the second version, and YOLO v3 and 4. They have a great number of improvements and tracks. This is the general pipeline of the YOLO v3. On the left side, there is a demonstration of the representation of the output of YOLO v3 feature map. In each feature map, for each cell, they contain 3 bounding boxes with their corresponding categories and their height, width, retail, and location. In figure 12, there is a big bounding box parameter transformation illustration. They using dimension priors and location prediction, allow mapping of non-constant positive predicted values to constant positive values. And the k-means algorithm is used to generate 9 prior bounding boxes. The model only predicts the ratios, not the absolute height and width. And finally, the non-maximum suppression, i.e. the NMS, used to filter the bounding box to get the final result. On the right side, we can see a graph demonstrate the advancement of YOLO v3. Now let's come to the YOLO v4. In this section, I will mainly focus on the mosaic augmentation, which randomly combine 4 images, but keeping their bounding box correctly, which can significantly enrich the dataset diversity and improve the generalization ability of the model. Now let's come to the fourth approach, the CenterNet, which is a standard anchor-free approach. It is an end-to-end framework. They use a Gaussian kernel to build the ground truth and perform regression. They also use the max pooling as non-maximum suppression to reduce the inference time. For recent works, I will focus on open world object detection. The one is detect clip, and another one is YOLO world. For the first one, open world object detection, more in tune with human habits of perception of the world. And for most of datasets, they only contain limited class number. For example, the MS COCO only contains 80 classes. As for this approach, it has a very impressive zero-shot ability. By utilizing the clip, the contrastive language image pre-training, it enables the unlimited class numbers and categories. And here is open world object detection for another open world object detection approach, the YOLO world, which is published recently on arXiv. By comparing with the previous approach, it has a better MAP, the mean average precision. Illustrated in the paper, it has a 20 times speed up compared with the previous approach, but with a better accuracy. For example of the open world object detection, we can see there are many categories we didn't see in a common object detection dataset. We demonstrate a very nice and impressive zero-shot ability. That's all. Thanks very much.